So good evening everyone. Yesterday we have started with this nuclear magnetic resonance spectroscopy, and over here we have seen that all the atoms they are having this nucleus, and in the nucleus we are having protons and the neutrons, and if there is an excess number of the protons over there within the nucleus, and if the spin quantum number of the nucleus is coming out to be I equals to half, which basically comes from over here when the number of the protons and the neutrons among either of these, one is odd and the other is even in number. In that case we can have the spin quantum number as either as half, 3/2 and 5/2. So among all of this, the protons which are having, or the nucleus which is having spin quantum number as half, they are NMR active. Some of the common atoms they include H1, C13, F19 and P31. So these atoms they are NMR active. On the other hand, if both protons and the number of both protons and neutrons they are even, or both of them are odd, in either of these cases the system they are not NMR active. The atoms are not NMR active. In other words, they are NMR inactive. Okay. And then we have seen why this is so, and we have also discussed that suppose when there is no field, there is all the atoms they are at the same energy level and delta E is equal to 0. However, if we increase the magnetic field B0, then there exists two states. Once the lower energy state, it is the alpha state, and the higher energy state, it is the beta state. Okay. Next, we were to discuss about why should the proton nuclei in different compounds they behave differently in the NMR experiment. In our last class, we have discussed that when we talk about an atom, atoms they are composed of protons, neutrons which are present within the nuclei, and apart from that we have electrons. Okay, so if you look into the architecture of any atom, suppose this is the atom, the whole atom. So over here the red region, it is the nuclei on the nucleus, and these blue dots they are the electrons. So these blue dots they are also present over there, and when we are applying a magnetic field B0, what we were discussing in our last class, we were discussing that the protons they are charged particle and they start precessing. Okay, now due to the precision there is a generation of a local magnetic field. However, we need to remember that the atoms they also consist of these electrons which are again charged particle. Right? Now since they are also charged particles, they will also start moving, and while they are moving, these electrons they will also create a local magnetic field. Now this magnetic field which would be created that would oppose the applied magnetic field. Okay, so suppose B dash, it is the B0 dash, it is the net magnetic field which is being exerted onto the this proton. Okay, that would be given by B0 minus of delta B. Now delta B, it is the small magnetic field or the local magnetic field which is being created by the movement of the electrons. Okay, so if you see over here, though we have applied a magnetic field of B0, we are having a local magnetic field which is being exerted by the moving electrons, and thereby the resulting magnetic field which is being applied onto the protons, it is lesser than B0, and this process or this phenomena, it is regarded as shielding. Okay, this is regarded as shielding. So since we are applying the magnetic field, so it is called shielding of the magnetic field. Okay, so the magnetic field over the proton, it will be, or in other words you can say that the protons will be shielded or being saved from the external magnetic field B0 to a certain extent due to the movement of the electrons. Okay, now this region, this curve or this graph, this curve, it shows the NMR spectra of the protons, NMR spectra of the protons when they are attached to different functional groups. Okay, now if you see over here, our origin 0 0, it starts on the right hand side, and as we move towards the left, the value increases. Okay, now this 0 0 value, it has been reserved for the proton spectra of trimethyl silane. Okay, so this is TMS, which is regarded as the trimethyl silane. Okay, so this 0 0, it has been reserved for TMS. Okay, and this TMS, it is highly shielded region. Okay, the protons in this TMS, they are highly shielded. Okay, and because of that reason, we get a very strong peak over there. Okay, now if you see, if you look over here, I have told that this 0 0, it is for the high field region. Okay, and as we move towards the left hand side, it is for the low field region. Okay, now the question arises, just few moments back I told you, when there is a shielding, this net B0, it increases. Sorry, it decreases. Okay, the net B0, that B0 dash onto the atom or onto the proton, it decreases due to the movement of the electrons. Now, why this is so? This we will be understanding a few moments later, and why this is happening. Okay, now let's go to the next slide. So suppose we are applying the field and this is the permanent field B0. Okay, now we know that there are two states. One is alpha state and the second is the beta state. So the alpha state, in the alpha state, the net magnetization vector would be in the direction of the B0. So let me write it as B alpha. On the other hand, the magnetization vector for the beta state, it will be opposite to B0. Okay, so let me write it as B beta. Okay, under normal circumstances, as I told you, that the number of protons that are in the alpha state, they are slightly greater than the number of protons that are in the beta state. Okay, now due to this reason, what happens is that there is a net higher number of protons which are in the state. Okay, so I hope you have understood what I mean to say. So in general, due to this reason, since B alpha, it is in the direction of B0, we will be having a net magnetization vector due to the protons in the direction of the B0, due to the presence of alpha state protons in slightly higher number as compared to the beta state protons. Okay, now we have talked about this. So we are expecting that this magnetization vector within this magnetic field would be in this direction, perfectly aligned. That's very good. Okay. However, just now we have discussed about the presence of electrons within the atoms, and which will affect the net magnetization vector which is being sensed by the protons. Okay. In that case, what will happen? So this is in the direction of this black arrow, it is in the direction of the magnetic field. However, the beta state, as I told you, if I show it in the using this blue mark, it would be in the opposite direction, right? But our protons, due to the shielding effect, neither they will be in the alpha state completely, nor they will be in the beta state completely. Okay, so what would happen? They will be having a net magnetization vector somewhere in somewhere else direction. Okay, so neither it will be in favor of the in the direction of the B0, nor it will be in the direction against the direction of the magnetic field or the B0. Okay, and this blue line, it is due to the shielding effect. Okay, and this black line, this is due to the de-shielding effect. Okay, so shielding effect and de-shielding effect. Now let us understand about the Nmr instrumentations in very simple words. As I told you, there will be a sample holder. Over there we'll be having the sample. Then we'll be having a strong magnetic field. Then we will be having an RF transmitter, and then we'll be having an RF receiver. Okay, as I told you, this RF transmitter, it will transmit radio frequency waves in bursts or in pulses, and during this off time, this RF receiver, it will be active and it will be receiving the signals from the sample. Okay. Now this RF transmitter and RF receiver, they are working in a single frequency. They are working in a single frequency. Okay. So there is another term which is called Larmor frequency, which is given by omega naught equals to gamma B0. Okay, so this Larmor frequency, what is this thing? We were talking about the proton, they are moving just like a top. Now when they are moving, the frequency of the movement is this proton at a particular magnetic field B0, it is given by the Larmor frequency. Okay, so for a particular magnetic field, we need a the protons will be precessing at a particular frequency. Okay. Now the absorption of the radio frequency by the protons will only happen at Larmor frequency. Are you getting my point? So what I mean to say, we are having this proton, it is moving, it is precessing, and while it is precessing, it is having a frequency, and it will precess at a particular frequency only at a particular B0, which is equivalent, which is specific for a particular atom. Okay, which is specific for a particular atom. Okay. Now, if you see over here, there are two variables, omega 0 and B0. If you look into the instrumentation, basic instrumentation of the NMR instrument, as I told you, this RF transmitter and receiver, they are working in a single frequency. Okay, so that means if you look over here, I told this Larmor frequency is specific, this B0 is specific for a particular atom, and this B0 would vary for each and every atoms, and also for each and every what you call molecules. Okay, so what happens over here is that if you look over here, so we are having this atom in the alpha state, this black line. However, when we are irradiating this sample with this RF pulse, it has to be in this alpha configuration always, so that it can receive this radio frequency, and by absorbing that radio frequency pulse, it will go to the beta state. Okay, so from here to here it is possible. However, from the intermediary step, just like in the shielded region, it is not possible. Okay, so what we need to do, we need to bring this, or we need to negate this shielding effect. Now, how will you negate this shielding effect? If you go to the previous slide, over here we have said that this B0 minus delta of B, and this minus delta of B is due to the electron, and we have to negate this. But can you negate this? It is not possible. The reason being, the electrons are the integral part of the atom, so we cannot remove those electrons from the system. So avoid this, or to overcome this, not avoid this, to overcome this, what we need to do? We need to increase the magnetic field. So let me write this equation. I'm writing this equation over here. So B0 dash equals to B0 plus, B0 minus delta B. Say for example, I am writing it as electron, for electron delta BE. Then we have to apply another set of magnetic field. It's called delta B A for applied. So we need to apply another delta B A, which will cancel out this thing, and we will be getting the effective B0 onto the proton. Okay, so because of this, for increasing this, we have another set of coils which is connected with a sweep generator, which will slowly increase our magnetic field within the sample, and that will help us to bring the protons which are neither in the alpha state or in the beta state in the shield due to the shielding effect to the alpha state formation. So basically this sweep generator, this magnetic generator, which is a variable magnetic generator, the first one, these blue lines, this blue north and south, they are fixed ones, and that is totally, no, what you call, that is that we call as a permanent magnet system. However, the non-permanent magnet, which is helping us to sweep the magnetic field or increase the magnetic field in small incremental manner, they are non-permanent magnet, and this non-permanent magnet, it helps us in overcoming the local magnetic field exerted by the electrons, and thereby they help us in bringing these protons into the alpha state. And once it is done, now this RF transmitter, since it is a single frequency stuff, it will be now able to excite the protons, and while they are exciting it, it will go to the high energy state, that is in the beta state. Okay, is it clear to all of you?
Yes, sir.
Yes, sir.
Yes,
Yeah.
sir.
Okay. So now let us look into this in from another angle, another perspective, basically. So there is a 3D plane, okay, and we are applying B0. Sorry. In the direction of Z. Okay. Now, as I told you, these atoms, if you are talking about this alpha direction, it would be something like this, the net magnetization vector. If it is in the beta state, it would be in the downward direction. Okay, basically it will be cancelling out the beta 0, and then say we have the ideal conditions, usually in the ideal condition, it would be something like this. Somewhere it is like this. Okay. Now, as I told you, this is the shielded atom. Now, to this B0, we need to apply delta B in incremental fashion such that it moves in the direction of the B0. So when we start increasing this delta B, it will slowly go on and it will come to the Z axis. And once it is on the Z axis, then we apply radio frequency pulse. And when we apply this radio frequency pulse, it flips 180 degree and it goes to the beta state. And when it has gone to the beta state, then as I told you, these RF pulses are momentarily for a very small time. So when we stop this, now these atoms, it goes back to its alpha state, and while it is going back, it releases the absorbed radio frequency. Now this radio frequency, as I told you, these are a single atom can absorb only a specific radio frequency wavelength or frequency radio frequency waves. Okay, single wavelength or single frequency radio frequency waves. Okay, so next is, as I told you, I am telling you that it will be in a what you call, in a slanted position, somewhere in between alpha and beta position, and then it will directly flip to the beta, and then again it will come down. But it is not the case. When I talk about precessing, if you have seen a top, it does not move. Most of the time it does not move in a straight way. Basically, it moves in a what you call elliptical or a circular manner. Okay, so this happens over here also. When it moves, when these spinning atoms, they are moving in an elliptical manner, and then they come to the position. So when they are having high energy, they are having a higher base, and slowly it loses its energy, and when it comes to this B0 plus delta B in this thing, and they become parallel to the Z axis, that means they come to the alpha state, then they are having this thing. Then they are having the lowest energy. Okay, so I hope every one of you understood about the de-shielding and the shielding phenomenon. So when there is a shielding, we need a high magnetic field. Okay, see, it is written over here, high field region. Okay, so be very careful what the other person is telling you, whether it is whether it is about the shielding effect, or you are talking about this high field region, or whatever. So you need to understand this concept. Over here I have told that the moving electrons, they are generating a delta B, which is negating the effect of B0, such that the nucleus it is experiencing a lower magnetic field. Okay. However, when we talk about this NMR curves, over here you need to understand that we have to supply an additional magnetic field of delta B so that we can de-shield, or no, we can overcome the shielding effect of the electrons. Okay, and then from there we have to apply the radio frequency so that it goes to the excited state. And due to this reason, even though we are telling that the protons, they are shielded, at the same time we are telling that it is having a high magnetic field, or it is at a high magnetic field region. Okay. Now trimethylsilane, if we consider two atoms A and B and there is a lone pair between them, if one of them attracts this lone pairs is more electronegative, I mean to say, and since they are more electronegative, if they pull the electrons towards them, then comparatively the electron cloud on the A, it will reduce. If B is more electronegative, it will pull this lone pair of electrons towards itself, and the electron cloud over the A, it will be reduced. Okay. In other terms, the A will become de-shielded. Okay. Now, if you look into the TMS, trimethylsilane, and we have discussed that we will be talking about this hydrogen atoms, or we are interested in the H1 NMR. Okay, in H1 NMR we are basically interested in the absorption pattern of the protons. Okay. Now, if you see over here, if you look into the carbon and silicon, they are both of them, they are having nearly equal electronegativity, and hence this carbon atom, the electron pair between this carbon and the silicon, the electron cloud is well distributed. They are not, the silicon, it is not driving the electrons towards itself, and due to this reason the hydrogen atoms over here in the methyl groups of the TMS, they remain shielded. Okay, they remain shielded. Okay, and all these atoms, they are these hydrogen atoms, they are facing same or similar environment, and due to this reason you will get a sharp peak for these hydrogen atoms, and it will be basically 12 times, because we are having 12 hydrogen atoms, so we will be getting a very sharp and very what you call intense peak for the TMS. And due to this reason, this TMS, since it is highly shielded, we take it as an internal standard. And we consider the peak of the TMS as 0. Okay, and with respect to TMS, we find out the this the shift of the other atoms. Okay, so if you see over here 215 hertz, that means there is an increase in the there is a shift in the magnetic pattern. Since there is a shift in the frequency, there is a shift in the magnetic pattern. So you can measure the things in two ways. Either you can keep the magnetic frequency fixed and you vary the magnetic field, and the other thing is that you fix the magnetic field and you increase the frequency. However, in most laboratory laboratory NMR machines, they have a fixed frequency and the magnetic field is being what do you call, it is being varied using the sweep generators. Okay, now over here, if you consider this ketone, this oxygen is electronegative, so it will pull in the electrons from this carbon atom, and in turn this carbon atom, it will pull in some of the systems over here, some of the electron cloud from here, and accordingly the electron cloud over this hydrogen atoms will be decreased as compared to the TMS, and hence there is a slight shift. Okay, now in the case of this CCl2H2, the electron withdrawing groups, they are directly connected with the carbon atoms. So the electron cloud from the hydrogen atoms, it will be markedly pulled by this carbon atoms, and hence this becomes more de-shielded, and hence there is a what do you call, larger shift. That means you are going towards the lower magnetic field region. As you see over here, we are coming to the low field region. That means you need a lower B0 plus delta B to bring the proton atoms to the alpha state. Okay. Now again, if you look into this benzene ring, we all know that within this benzene ring there is electron cloud and there are certain unsaturations. So this benzene ring is basically electron hungry, and due to that reason it will pull the electron cloud towards this central region, and due to that reason, if you see the peak for the benzene protons, it will be at the lowest magnetic field. Okay, it will be at the lowest magnetic field. So a reference standard should be chemically unreactive and can be easily removed from the sample after the measurement. Also, it should give a single sharp NMR signal that does not interfere with the resonances normally observed for organic compounds. Tetramethylsilane, usually referred to as TMS, meets all these characteristics and has become the reference compound of choice for proton and carbon NMR. Okay. Now let us look into the NMR spectra, how the NMR spectra are being generated. So if you see this zero means over here we have got the TMS spectra, TMSP. Now for this ethanol, if you see this H atom, so this blue, there are 3 atoms. Now for these 3 atoms, if you see, you have got 3 peaks. So is it due to these 3 atoms? No. It is basically the coupling of these hydrogen atoms with the green hydrogen atoms. So we need to look into the neighboring hydrogen atoms. How many neighboring hydrogen atoms are there? In this case, there are 2 neighboring hydrogen atoms. So the rule is that since these blue hydrogen atoms, they are in the similar chemical and the magnetic environment, so they will be considered as one, and the splitting of these peaks would be as per the available neighboring hydrogen atoms. In this case, it is 2 plus 1. So accordingly, you have seen that for these blue hydrogen atoms, you have got 3 peaks. Now coming to the green hydrogen atoms, The neighboring hydrogen atoms are, there are three numbers of hydrogen atoms, neighboring hydrogen atoms, which are basically the blue one. So 3 plus 1. So if you see, we have got 4 numbers of the splitting. Okay, 4 numbers of splitting. Okay, so for the green one, even though we are having 2 hydrogen atoms, we have got 4 peaks, and those 4 peaks denotes that in the surrounding of this hydrogen atom there are 3 hydrogen atoms. Okay, now for this hydrogen atom, if you see, in between we are having this oxygen and this hydrogen. Okay, another important thing, we would have expected that for this CH2 protons, these green ones, we have got 4 peaks. However, this hydrogen peak, this red color hydrogen, that would have also interacted with these 2 hydrogens, and instead of this one, each of these peaks would have been again having 2 peaks, but that is not the case. Okay, so that is called doublet of quartlets. So that means what I told you, for each blue lines for this hydrogen atom, we would have expected another doubling. So doublet of quartlet. So doublet means double. Doublet means doublet of quartlet means we already had 4 peaks. Then these 4 peaks would again break into, each of these peak would break into 2. So 2 multiplied by 4. So we would have got 8 peaks. But that is not the case. Why? This is because this acidic hydroxyl proton group, it undergoes intermolecular exchange, and due to this reason there is a loss of coupling information. And due to this same reason, if you see this hydrogen peak, since there is a loss of the coupling information, it is also affecting over here also. Okay, if you see, you have got this hydrogen atom. Okay, now coming to the what should be the peak height. The peak height, it is given by this Pascal's triangle, which gives you about the intensity ratio. For singlet, if there is a single peak, you will be getting the intensity ratio would be 1. For 2, if there is a doublet, it would be 1:1. For triplet, it would be 1:2:1. So if you see 1, this is 2, this is 1. However, in practicality, it will be nearly to this ratio. If you see, if you consider it as 1, the other one is slightly lower than 1. Okay. However, on roughly you can say it, the triplet peaks would be in this, the intensity of the triplet peaks would be in this ratio. Then for the quartlet, this is a quartlet, see 1:3:3:1. Okay, so accordingly, if you see, if you measure, it would be roughly in that region. And then if you go for the quintet, sextet and septet, accordingly your this will vary. The intensity ratio of the peaks will vary in that way. Now coming to the understanding of how this works, I have already told you that how it works, but let us again see it with the help of this schematic diagram. As I told you, there would be magnetic poles. These are giving you the, basically they are giving you the B0. Then you have the sweep coils, which is connected with the sweep generator. So it will be generating the delta B magnetic field. Then you have a radio frequency transmitter. So you have this tube sample holder, which is being spun continuously so that you get an average readings. Then you have the radio frequencies transmitter. This is red one. It will transmit the pulses, and close to these samples you will be having the radio frequency receiver and amplifier, and then you have this control console and recorder which will be recording the system. Okay. Another important thing I forgot to mention over here. Say there is a chemical compound CH3 CH2O CH2 CH3. So in this case, if you see up to this part, it is okay. Both are similar. Okay. So in that case, what will happen? So however, if you see there are two CH2 and there are two CH3s. So definitely you will not get this red peak system. You will be getting this blue and the green peaks. But these peaks, they will be somewhat broader in nature. And this is called peak integration. The reason being, even though we are telling that this CH2 and this H2 of the CH2, they will be at the similar environment. However, at the microscope, at the very small level, at the what you call electronic level, there would be some minor deviations, and the peaks may not appear at the same place, and you might be having very small distance between the observation of these two peaks. Okay. However, the current day NMR spectroscope, they are not having so high resolution, and due to that the reason you will be able to see broad peaks. So you will be getting three peaks for these blue hydrogen atoms, CH3 hydrogen atoms. However, these peaks will be slightly broadened, and this broadening is due to the peak integration phenomena. Okay. I hope all of you have understood what I have tried to convey to all of you.